Hello, scientists. Caroline here. What does the surface of the moon look like? You probably remember from studying the moon in a previous lesson that its surface is covered in craters. What you might not know is that the largest crater on the moon, Aitken Basin, is over 1,600 miles across. What forms massive craters like these? Usually, they are formed from collisions with debris objects, such as asteroids or comets. And without an atmosphere to protect it, the moon gets hit with a lot of asteroids. What do you think determines the size of the crater formed by an asteroid? Its mass and speed might seem like obvious choices. Other things like shape and composition would matter too. It's a rather complicated equation. Today, you'll do a hands-on experiment to focus specifically on how the mass of an asteroid affects the crater it makes. If you're hoping for a science field trip to the moon to test this, sorry, but that won't be necessary. Instead of observing an actual asteroid impact, you'll drop a lightweight ball and a heavier ball into a pan of flour to make craters. The good news is that you can do this lab right in your own kitchen. Oh, before we get started though, there's some important background information that we need to cover. Because when I was your age, I did a very similar experiment, though I didn't do it very well. Let's start by finding and learning from my mistakes so that you don't repeat them. When I did my version of this experiment all those years ago, I dropped a small rock into a bowl of flour, then threw a large rock as hard as I could into that same bowl of flour. I was pretty sure the larger rock would make a bigger crater, and I wanted to make sure it had enough speed to do just that. Sure enough, it worked. I concluded that larger rocks cause bigger craters than smaller rocks. Unfortunately, my teacher wasn't impressed and said my results weren't valid. What did I do wrong? Pause the video for a moment and see if you can spot my mistake. To understand why I received a disappointing grade on this science experiment, we need to define some terms. We'll start with the dependent variable. I like to think of the dependent variable as what we are measuring. You might also think of this as the results or data you are collecting. And there's a good chance that the values of the dependent variable might depend on other conditions in the experiment. Hence the name. If we're dropping objects into flour to study the craters they form, what do you think the dependent variable is? What will you likely be measuring and recording as data? The size of the crater, because it will likely depend on other factors that you set up. Of course, you could measure the size of the crater as either the width or the depth. In fact, knowing both might be useful. So the dependent variables for your experiment today will be crater width and crater depth. The other variable we need to be aware of is our independent variable. This is the factor you are testing, and often the part you have some direct control over, which is why it's called the independent variable. What factor will you test in your experiment today? The mass of the asteroid. You'll intentionally pick two balls with different masses so that you can compare the craters made by each. Therefore, mass is the independent variable. Of course, we could have chosen to test something different, like the velocity of the asteroid at impact, or the shape of the asteroid, or the material of the surface it impacts. Any of those would have made a good independent variable. But here's where I went wrong with my experiment before. Unlike the dependent variable, we can only change or test the values of one independent variable at a time. What independent variables did I change in my first attempt at this experiment? For one, my rocks not only had different masses, but they had different sizes too. So was it the mass of the larger rock that caused the larger crater, or did it only make a larger crater because it took up more space? And because I dropped one rock but threw the other, they also had different impact velocities. Maybe the increased velocity was more responsible for the larger crater than the mass of the rock. There's no way to know, So today you'll only be testing the mass of the asteroid, or in our case, the mass of the ball, and leaving both the size and velocity constant. This is the only way to ensure our results are valid. To see how the mass of an asteroid affects the impact crater it forms, you'll use 2 different balls and a flour-covered surface to simulate impacts. This experiment will model how asteroids create craters when they collide with bodies in our solar system, such as the Aitken Basin crater on the Moon, as well as craters formed on Earth and other bodies in our solar system. To perform the experiment, you'll need some materials. Check to see if you have these at home. First, you'll need 2 small balls to represent the asteroids. One should have significantly more mass than the other, but they should be approximately the same size. A baseball and a pickleball will work well, but feel free to use any other combination that works, such as a ping pong ball and golf ball. You'll also need a bag of flour and a bowl or pan to place it in that is several inches deep. Your pan should be made of either plastic or a sturdy material that won't break in case of an accidental collision with our asteroid. Finally, you'll need a ruler or tape measure and something to help you smooth out your flour surface, such as a spatula. Before you continue, pause here to read over the safety information, materials, and lab procedure in your interactive lab notes with a parent or guardian. Make sure you have their permission and all the required materials before continuing. Oh, and this lab could get messy, so either cover anything important nearby or move your workspace outside. And know that your clothes will get covered in flour, so dress accordingly. Start by placing flour in the pan. Make sure the flour is at least a few inches deep. Use a spatula or other flat utensil to smooth out the surface so that it's mostly level, but don't pack the flour down too much. It should still be soft and fluffy on the surface. Before we start collecting data about the width and depth of the craters, we'll first gather some qualitative data about an impact. Qualitative data includes observations that don't involve numerical values, only descriptions. This type of data can help us understand how processes work. To visualize the process of crater formation, cover the surface of the flour in a thin layer of cocoa powder. This will help you see how much previously underground material is uncovered and brought to the surface as a result of the impact. Hold your baseball, or heavier asteroid, several feet above your pan. Make sure you are lined up as close to the center as possible, and when you are ready, drop. Pause the video here if you want to try it for yourself. Carefully remove the baseball. What do you notice about the patterns that the cocoa powder and flour made? Was the surface disruption more dramatic than you expected? This demonstration gives us a small glimpse of how high-speed collisions can be so destructive to the surface of a planet. Now let's gather some quantitative data about crater formation. Quantitative data includes observations that use numerical values, such as measurements of distance, mass, speed, and so on. Start by using your ruler or tape measure to designate a location that is approximately 4 feet above your pan. Be sure to smooth out the surface of your flour if necessary. If you still have cocoa powder on top of the flour, it's okay if it gets mixed in now. Hold both your heavier and lighter balls at the designated height, being careful to line them up so that they'll both land in the pan. Then, asteroids away! Let them drop simultaneously. You should now have 2 craters in your pan. If anything went wrong, you can always try again. Let's measure the width and height of the craters. Make sure you measure the widest part of the crater if it isn't symmetrical. In the sample experiment shown, the baseball made a crater that was 9 centimeters wide, while the pickleball's crater was 6 centimeters wide. Now measure the depth. Be sure to measure from the deepest part of the crater to the surface. Our sample baseball's crater is 3 centimeters deep, and the pickleball's crater is 2.5 centimeters deep. Pause the video here if you want to try it for yourself. my teacher would have trusted these results a little more than what I had before, simply because we were careful to only change one independent variable, the mass. But there's still something else we could do to make this data even more reliable. Any ideas? When you first started this experiment, you may have found that you had to try dropping the balls several times to get good results. Maybe sometimes you aimed wrong and it didn't hit the bowl at all, or maybe you hit the side of the bowl first and took a funny bounce. If you know that something went obviously wrong with your trial, you should do it again and not count those results. But for all the mistakes you see and notice, there could be others that are hidden from you. Maybe the surface of the flower was a little uneven one time, or maybe your hands weren't exactly at the same height, or maybe a gust of wind threw our asteroids just a little off course. How can we possibly account for all these little sources of error if we don't always notice them? The best way to make up for this is to do multiple trials. This way, if the data from one trial was just a little off, there are other data points to lessen the impact of the mistake on our results. You've already dropped the heavy and light asteroids once, you just need to do that again. And again. How many more times? Well, the more trials, the more reliable our results will be. But for our purposes, 3 trials of each would be reasonable. Let's count the ones you already did as trial 1, then do a trial 2 and a trial 3 for both the heavy and light asteroid. After completing the trials, you can calculate the average width and depth for each based on the 3 trials. If you need help with this step, be sure to see the hints in your lesson notes. Pause the video here if you need to, and repeat all of your steps 2 more times for each asteroid. Come back when you have all your data. So what can we conclude? Pause the video for a moment and look at your data. Record any trends you see or conclusions you can make from it. My larger crater was made by the more massive asteroid model. This was true for both the crater width and depth, even when comparing the average of all 3 trials. This probably didn't surprise you. But what about the differences in crater size between the 2 asteroids? Did you expect the difference between them to be more extreme? Or maybe you thought it would make less difference than it did. And what about the differences in the crater width versus the crater depth? Did one seem more affected by the mass than the other? The sample results showed that the crater width was strongly affected by mass, while the depth didn't change as much. But your results may have been different, and that's okay. How much the mass of the asteroid affects the size of the crater depends on many factors, but experimentally we can show that mass does matter. Even when all other variables are held constant, more massive asteroids will do more damage to the surface than less massive ones. Unfortunately, we won't be able to go back in time and observe the asteroid that made the Aitken Basin crater on our moon. But scientists study and measure the crater it left behind. And by running simulations similar to what you did today, they can get an idea of what type of asteroid would have made such a massive dent in the surface. Okay, their simulations are probably a little more complex and don't involve bowls of flour, but it's the same idea. That's it for today, scientists. Hopefully you didn't make too big of a mess in your kitchen, but if you did, go clean it up. Be sure to finish the lesson activities so that you can practice identifying variables and learn more about impact craters along the way. Don't forget to keep watching the skies and marveling at our universe. See you next time! Hey, hey.